In this video, I'm going to talk about a hypothesis test. The thing about hypothesis testing is that the details make it so unbelievably complicated. It's like a lot of mental juggling. It's hard to tell what's going on and keep track of everything. And it's too bad because the idea of a hypothesis test is actually so logical and so basic. It's when you add the details that you can't really tell what's going on. So in this video, I'm not going to talk about details. I'm just going to give you kind of a basic idea of how you conduct a hypothesis test. And hopefully once you understand the idea, the terminology won't be so crazy. All right, so what is a hypothesis test? You want to check whether or not the assumed mean is true. For example, let's say that you take a sample and you calculate the mean, and that mean is way different than supposedly what the population mean is. At what point do you decide then to say that the assumed mean must be wrong? That's where all the work goes into finding that point. At what point is different too different? So let's say you take a sample and you see where that sample falls under the bell curve. I mean the mean of the sample. You take a sample, you calculate the mean, and now you see where it falls under the bell curve. So let's say that I did that, and my sample mean happens to be where this blue X is. Well, that doesn't seem too bad, right? It's kind of close to the mean. I'm assuming that the distribution follows a bell curve, and I'm assuming that the true population mean it goes right in the middle of that bell curve. But what if instead of this happening, I would have taken a sample, I would have calculated the mean, and then I would have seen where that mean falls under the bell curve. That would end up way over here. Now I have to think about this. I have to ask myself, yes, maybe my sample just happened to produce a mean that's way over here. I mean, that's certainly possible, but it's not probable. So that's what a hypothesis test is. You have to decide specifically and explicitly when is different too different. And that's what we're going to talk about. Originally, you would pick a percent that is rare enough. For example, let's say that you set your rare enough value at 2%. That means that if your sample produces a mean, that you would only expect 2% of samples to be that far away from the true mean. You decide that the assumed mean must be wrong. Again, this isn't 1000% true. It's just that if you take a sample, you calculate the mean, and that mean is so different than the assumed mean that you would only expect, say, 2% of values to be that different, that's when we say, well, maybe the assumed mean is wrong. Based on my sample, I have to say no way on that, on the assumed mean. So sometimes, here I just said 2%, but depending on the problem, you might be willy-nilly and you might say, well, if my sample produces a mean that I would only expect 10% of values to be that different, I'll throw away the assumed mean. Or maybe you're very cautious and hesitant for whatever reason to reject the assumed mean. Then you might say, well, I'm only going to say the assumed mean is wrong if I get something really extraordinary. If I take a sample, I compute the mean, and it happens to be a 1% chance that my mean is that different than the true mean, only in that case will I reject the notion that my mean is correct, my assumed population mean. Just for this example, I decided to pick 2%. But you'll see in different problems, they're going to give a different percent. This is what they mean by level of significance. A 10% level of significance is kind of big, and it just means you're kind of, you don't have too many hang-ups about tossing the assumed population mean. But a level of significance of 1% would mean, no, I want to be really sure. I'm only going to throw away my assumed population mean if there's a 1% chance that my mean just happened to be this different. Okay, so let's say, just for for sake of argument, that you think the true mean is actually bigger than the assumed mean. So originally what you would do is you would calculate a critical value. That critical value is exactly where you separate the bottom 0.98 area from the top 0.02 area. That's for a 2% level of significance. What you're going to do is you find this cutoff point. It's here in a blue asterisk. And in this cutoff point, 98% of all the sample means that you would get, 98% of all the means, 98% of all the samples you take, and if you calculate the mean, you would expect 98% of them to fall in this blue area. You would only expect 2% of samples to fall in this red area. This is the original way that people kind of thought about testing a mean. First, you would decide on a percent. Once you decide on a percent, you calculate this critical value, this tipping point. This tipping point is where you say anything beyond this critical value is a little too coincidental to just happen to happen. If I get a sample and I calculate the mean, and my mean falls way over here where the red is, I'm going to say that my assumed mean is probably wrong. Yes, there's a chance that a sample is going to have a mean that's beyond the critical value, but it's only a 2% chance. And based on how rare that is, I'm going to instead decide that my assumed mean must be wrong. So this is what they call a right-tailed test. It's when you think that the true mean is actually bigger than the assumed mean. So you would want to calculate the critical value that separates the top whatever percentage of extreme values. In this case, I picked 2%. And if you had a left-tailed test, let's say you think the true mean is smaller than the assumed mean, then the critical value would be the value that separates the bottom 2% from the top 98% under the bell curve. What if you don't specifically think that the mean is greater than or less than the assumed mean? What if you just think it's different? You want to test if it's different. In that case, you're going to come up with two critical values, a positive one and a negative one. You would split up your level of significance into a left tail and a right tail. This is what they call a two-tailed test. So if you have a 2% level of significance and you're conducting a two-tailed test, here are your critical values. It would be on the left, this critical value separates the bottom 1%, and this critical value on the right separates the top 1%. And you say if anything falls in this blue area, I take a sample, I calculate the mean, and it falls in this blue area, that's the middle 98% of the bell curve, then you're going to leave it as is. But if my sample mean happens to be so extreme that only 2% of all sample means would be either that big or that much bigger or that much smaller than my assumed mean, 1% being that much bigger, 1% being that much smaller, so a total of 2% would be that different, then you would reject the sample mean. So that covers the critical value approach, but we don't really use the critical value approach anymore. With the critical value approach, you have to calculate those tipping points, and that's going to be unique to every problem. Well, there's another thing that you can focus on where you don't have to come up with the middleman. Instead of focusing on those tipping points, let's instead focus on the area beyond your sample mean. So for example, let's say that you take a sample and your sample mean falls right here. What does this area in blue represent? For argument's sake, let's say that this area is 0.12. That means the area to the left of it is 0.88. What happens if the sample you take has a mean that's further away from the assumed population mean? What happens if the sample you take is more on the fringe of my bell curve? So in this example, look where my sample mean is. It ended up leaving an area of 0.12 beyond it. But what if, in a different problem, I take a different sample, and it ends up being lower than the assumed population mean. What happens to the area beyond where my sample mean falls under the bell curve? It gets smaller. This area is exactly the p-value. The p-value is just an area. And the further away your sample mean ends up under the bell curve, the smaller that p-value is going to be. In this problem, or in this example, what does a p-value of 0.05 mean? That means that you only expect 5% of samples to produce a mean that's at least this far away from your sample mean, or from your assumed mean. So that's why a really small p-value means that your assumed population mean is wrong. A p-value of 0.01 means that there's only a 1% chance that, assuming your population mean is correct, there's only a 1% chance that you take a sample, that you then compute the mean of that sample, and that sample is going to be that far away from the true population mean. There's only a 1% chance that that would happen, that it would be that different than your assumed population mean. That's what a p-value is. And that's what's nice about a p-value, is you don't have to compare your z-score, your t-score to your critical value. It speaks for itself. When you think about a p-value, if I tell you that I took a sample, I computed the mean, and it gave me a p-value of 0.000001, I don't really care what the critical values were. I just know that there's a super tiny fraction of a chance that my sample just happened to produce a mean this different than the true mean. So that's what's nice about a p-value. You can think of it as a percent, and a p-value of 0.01 means that there's only a 1% chance that your sample mean happened to be that different. So with that, when you're doing a p-value test, let's say that you say, okay, I want to say that if I'm going to take a sample, I'm going to compute the mean, and if there's only a 3% chance that my mean happens to be this different from my sample, or from the true mean, that's your level of significance. You're going to say, I'm going to put up with a lot. But if something goes beyond, if something's so different than my assumed mean that there's only a 3% chance that that happened, you set your level of significance at 3%. Now, if your p-value comes out to 0.007, that means that there's only a 0.7% chance that your sample mean happened to be that different. So 0.007 is less than 0.03, and that's why there's that rule that you're always comparing your p-value to the level of significance, because the p-value is just the probability that your sample mean just happens to be that different than the true mean. This level of significance is just the level of coincidence you're willing to accept. So if you say, I'm going to say a 5% level of coincidence, that means that as soon as your p-value falls below 5%, that means that there's less than a 5% chance that your sample mean just happens to be that different than the true mean. At that point, you reject the assumed mean.